Professor, you're muted.
Now? Oh, no?
Now it's good.
Now it's okay.
Damn. Oh boy. All right, so as I was saying, you guys didn't hear anything which I said, right? From the
No.
beginning, obviously,
No.
obviously, yeah. Okay, so so depth first search and breadth first search are quite useful in many applications. Sometimes we combine these, for example, the DFS or BFS, we combine them with some other algorithms in order to solve certain applications in pathfinding and finding out, for example, like disconnected components and stuff. So, for example, DFS is usually used to find if you have islands of graphs in a graph forest. Usually, when you have multiple graphs, like this, so you have one graph, another graph, and another graph. People like you look at this, like you have many of them. So these are called this is called a forest or graph forest, where you could use DFS, for example, in order to detect like whether these guys are connected or not. So you detect these, like what they call islands, right? Or batches, whatever. For example, BFS, we use it in order to find the shortest path in a graph, right? So there are many interesting applications for BFS and DFS here. And what I wanted to say here is that depth first search is a generalization of a pre-ordered traversal of a graph. So pre-ordered traversal of a graph, right? So we, practically speaking, we process the vertex and then we recursively traverse all other vertices adjacent to that vertex, right? But here's the interesting part. There are a couple of points that we need to cover here before we actually, like, couple of keywords about what does it mean to visit a vertex or visit a node or explore a vertex or a node, right? So let's actually cover a couple of terminologies here. But before I actually carry on with that, hang on, let me actually write down this. We process or we explore, we explore a vertex, or we visit a vertex. Okay. Then we explore it. Recursively. I don't know what's going on right now. Recursively.
I'm sorry, but you wrote we a vertex.
Ah, okay. Thank you. We visit. A vertex. Then we explore it recursively. Then we explore its, let's say, its children. Recursively. Ah. Then once we reach to an end, we just simply backtrack and then we explore the other children, okay, or the other connections. So let's talk about the terminologies here. Excuse me. So, visiting a vertex. Visiting a vertex means that you just reached a particular vertex in a graph, or highlighting it, if you will. Okay, so that's what it means. It means that you have visited a vertex. Oh, sorry. Damn. Hang on. Sorry about that. It means that you have just reached a particular vertex. In a graph. Okay. Now you have this, and then you have exploring a vertex. And exploring a vertex is means that you visit all the adjacent vertices of a specific vertex that you are highlighting, right? So you are actually like you have like a bunch of vertices, right? Oh, it's glitching on me right now. Wow. Okay, and then for example, you reach here, and then you say, okay, I would like to explore this. Once you would like to explore this, you just simply visit this, visit this, visit this, and visit this, right? So you add these guys to a list, but you didn't process them yet, right? You just simply add them to a list. Right now, these vertices has been visited, okay? And then once you would like to explore them, you say, aha, okay, I will explore this right now, get me all of its connections, like it'll get me all of its nodes, okay? So this is the meaning of visiting versus exploration. Okay, so let me just write this down. Means you visit all adjacent or connected, if you want to, vertices of a specific vertex you are quote unquote highlighting, right? There we go. So this is what it means to visit a vertex. Now let's talk about like how this is working. So if you have like a bunch of vertices, so 2, 3, and then you have 6, and then you have 7, you have 4, you have 5, okay? Now, if you would like actually like to have, if you have a graph like this and you would like to do a DFS on it, what you will do is you'll say, okay, you will like enter from you, assuming that you are starting from 1. Then you will pick up at random. It doesn't matter which one you would like to pick. Doesn't matter which one you can actually use. You just simply say, okay, I'm going to explore either 5, 4, or 2. For the sake of the argument, I'm just going to pick up 2. Okay. And then you will figure out that, for example, 2 has already some other connection or some other adjacent vertices. And then you say, okay, I'm going to pick up arbitrarily one of those. So practically speaking, when you are exploring, you say, okay, right now we have the DFS, which I have right now, is 1, then 2, right? Then I'm actually exploring right now, let's say 3, for example, arbitrarily. It doesn't matter which one I pick right now. And I'm going to pick up actually 3. Now, when I realize that actually 3 doesn't have anything connected to it, so it's an actual like a dead end, I will just simply like traverse back or revert back to 2 and see what are other children or what other adjacent nodes that are being connected to it. So I say, okay, I'm going to explore one of them. So for example, I'm going to pick up 7, then 6, right? Because none of them still have anything in there. So there's nothing in there. And then 2 has been completely explored. This is it. You visited all the vertices, all the children of 2. 2 has been explored completely. And now you actually revert to 1, and then you actually start exploring, let's say 4, then 5, for example, right? So there you go. This is basically what a DFS would be. If we are actually talking about a binary tree, if you have, for example, a binary tree like this, so you have 1, 2, 3, and this we're going to discuss, I think, next week then. 4, 5, 6, and 7, and you would like to do a DFS traversal on this. It's actually called a pre-order traversal. So I'm just going to have DFS on that tree. And we're going to discuss what is a pre-order, post-order next time when we discuss binary trees. Pre-order traversal. And right now we're going to actually look, you actually like go from left to right, top down. So you go this first, then this, right? So it's going to be 1, then 2, 3, then 4, 5, 6, 7. This is what a DFS traversal will look like. Already Adil has covered with you, as far as I know, like the code and practical part. So you already like, I mean, no need to walk through it because you already got that side of the story. So yeah, this is practically it. This is what DFS is all about. Now, if you have something a little bit more complicated, like just to get the thing, like just to get the material complete, let's say. So if I have a graph that looks like this, then we have, why it is glitching so hard? 10, then let's say 9, and then we are going to have, oops, 10 and then 9, and then we have here 2, then let's say 7, and let's say here 8, 5, 6. Well, let's do some interesting connections here, and maybe even here. Okay, so let's say that you are actually trying to explore, to do a DFS as an example of this. So the DFS we usually use, in order to keep track of stuff, we usually use stack as a data structure. I mean, again, the implementation is actually quite, implementation details, we usually don't look at it in this subject per se, but it is actually just a, yeah, right now, like typically in books and the typical implementation would be just that we're using a stack. Maybe there are other techniques or other optimization techniques that people are using for probably any, depending on the implementation detail. but for the time being, we're going to actually be using a stack. And let me just demonstrate this like so, right? Or maybe even a little bit bigger. I don't know how long this will take. And right now, we're going to see that when you're trying, for example, starting from 1, you will discover that you have 4 and 2 as children. So right now, when you see that we have children or we have actually connections, we say, okay, let us in fact start exploring 1. So we push 1, so we keep track of 1. And then, for example, we pick up 4, for example. And right now, 4 has another children, right? Another child, which is, or another connection, which is 3. Right, so we need to keep track of 4 for now because we need to dig deeper, and we don't care too much like which one to pick right now. So I'm gonna pick up 4 and keep track of it, and then we visit actually 3, or we explore 3. So we visited 4, start exploring 4, and then we found 3. Then 3 has actually 2 children or 2 connections. Then we need to dig even deeper. Again, it's a DFS. So we actually keep track of 3, right, in a stack. And then we pick up, for example, it doesn't matter. We pick up, for example, 10. 10 doesn't have any children, right? So since 10 doesn't have any children, we just simply like say, okay, 10 is completely explored. We go back to 3. So we pop that out from the stack, right? And then we say, okay, is 3 is completely explored? And it's not, because we need it has another child, which is 9. So what we need to do is just push 3 back into the stack again, because we need to keep track of it, because we don't know if 9 has other children, right? And then we get back to the 9, and then we say, okay, 9 doesn't have any more children. We just simply gonna backtrack to 3 and pop it from the stack, right? So 3 is going to be crossed off. And then we say, does 3 have any more connection? It says, like, yeah, it has 2 to it, right? So we can actually keep track of 3 again. Excuse me. Keep track of 3 again and keep up with 2, right? Now, does 2 has any connections? It does. We need to explore. So we push 2 to the stack. And you actually go on so forth with that. So you start pushing stuff to the stack, and you pop them out. So you pop them out completely once they have been completely explored, right? So this 1 will be popped out completely once it's done exploration. Or for example, 4 will be completely popped out when we are done with exploring 4, right? So that's the most important thing. Okay, so I just simply like covered really quick, like just the steps, what's happening with this. So for example, like you go to 8, for instance, or 7, let's say. So 7, and 7 you discover it has other children, right? Oops. Okay. Yeah. So you explore actually, for example, 7, and then 7, it has other connections. So you say, aha, okay, I will pick up, for example, 5. So 7 is going to be pushed into the stack, and we explore 5. 5 has actually children, so it has 6. So we push out 5, push in 5. So we need to make sure that 6 doesn't have any children. 6 doesn't have any children. So 5 is completely, let's say, explored right now in this case. 5 has a connection to 7, so we actually ignore this because it has been visited already. 8 hasn't been explored. 2 is actually being explored, so we will not care about it. So in fact, 8 will be like we're gonna actually like keep 5 into the stack, and we say that 8 has been visited, right? And once you are done with exploring 8, you completely pop out 5. So we pop out 5, okay? And then you get back to 7, and you say, okay, what are the connections that hasn't been visited yet? And you discover that 8 and 5 has been visited. So 7 crossed out of the stack because it's been done. And 2 is we are already in there. It's already in the stack, so we should ignore it. And then you discover that 2 is already 2 is looking at 8 and 5, which has been completely explored. 1 is our starting node. 3 has been completely explored, so we actually crossed this out. 3 is already 2 and has been completely explored. 9 and 10 and 4 has been completely explored. And then you get to 4, which has been completely explored, and then 1 has been completely explored, right? And then you end up with an empty stack. So practically speaking, you just simply traverse the whole graph in that way. You just keep track of the stuff which you haven't completely explored yet, and leave backtrack and re-explore them again. Now again, this is the general guideline or the general look over the DFS, how it works. The implementation detail will differ a bit. So yeah, any questions so far?
No, everything is clear.
All right, so let's talk about then BFS. So this was DFS. Let's talk about BFS, which is the breadth first search. Now, breadth first search is is quite famous for. We use it sometimes for pathfinding. You can actually I think you can use it like if you have a map, a Google map, let's say, with the cities as nodes and you have the roads as connections and stuff like that. You could actually have. You could use actually BFS in order to find the path between two cities. So, but this is like I'll probably I'm gonna touch upon that in a minute or so, just to show you how this works. So it is used to explore nodes and edges of a given graph. So it's used. So let me actually write this down. It is used to explore nodes and edges of a given graph. Like this, so useful for pathfinding. In fact, I like if you are generating mazes or if you are generating a maze or if you are generating a maze or you would like, for example, to know if a maze is solvable, you could use DFS, and then you would like to know what is the shortest path through such a maze, you can use actually BFS, right? So DFS could be like to identify whether you have rooms or places that are unreachable, for example, right? This is actually quite useful, for example, if you are making, let's say, a game with a dungeon generation of some sort, you could make sure that just you have the rooms are connected with DFS, and then you say, okay, is the game is actually long enough or short enough, depending on what your parameters are, and then you pass that dungeon through a BFS and see how it will work. Okay. Let's see. We have got a. All right. So, in BFS, usually we explore, like, since I was just actually looking if we have any questions written, because I thought I had a written question. In BFS, usually we explore the children or the connections before we dig deep into the graph, right? So if we have the same from the previous example, right? like this, for example, in the DFS. So a BFS of this graph will be, usually we explore all adjacent vertices of a given node before going deeper in the graph. Okay, so this is how it will go. So for example, you pick up, let's say 1, and then you will say, all right, so the BFS, the birth first search result will be 1, and then you pick up whatever. So you pick up, for example, 5, then 2, for example, right? And then once you are done, okay, so 5 and 4 don't have any connections, 2 has, so it's gonna be like, then you actually pick up in whatever order you have. So 3, then 6, then 7, for example, right? Oh, actually, I made a mistake, by the way, regarding the DFS. I just realized that. Sorry about that. So a DFS in traversal in a tree. So I made actually, sorry about that. I apologize. This is my, yeah, this is a mistake. A DFS, a DFS pre-order traversal is not level order. So sorry about that. I really apologize. Because in a BFS when traversing a tree, it's actually a level order traversal, not a pre-order traversal. Not a pre-order traversal. Sorry about that again. So 1, 2, 3, 4, 5, 6, 7. BFS traversal of a tree is a level order. And I apologize again. So BFS is level order traversal in a binary tree, for example. It's the equivalent of that. So the BFS will be 1, 2, 3, 4, 5, 6, 7, right? However, in a DFS, it's a pre-order traversal, which will actually dig deep that way. So it's going to be 1, 2, then 4. Then nothing is in 4, then it will go back and then go 5. Then 2 is completed, so it will go back here and go here. So it's going to be 3. And then we go in, it's going to be 6. And then we traverse back, and then we go here, it's going to be 7. And you actually have traversed it all. Sorry, apologize. All right, so we have VFS done in this part. Let's actually look at the same example of a tree here. Oh, sorry, not of a tree, of this graph, which we had, like of this graph, right? Let me just push this down. So looking at this graph, so it's going to be, let's say, 1, 4, 2, then 3, 10, 9, 8, and then we have 7. This is connected, and this is connected with 5, connected, and then we have 6, for example. Okay, and you would like to do a BFS on this. what you're gonna do is in fact push this into a queue. So in BFS we use a queue, and then you'll say, okay, if my starting point is 1, okay, we're gonna just simply insert 1, and then we're gonna insert 4 and 2 because we explore all the connections before we actually we explore the node completely before we dig deeper, right? And then once you are done, you say, okay, sorry, not this is not like the queue. Like we can actually like say, okay, we push 1, and then we put here in the BFS result 1, right? And then we take 1 out, and then we start exploring it, 4 and 2. So we put 4 and 2. So you actually, has been actually crossed out. So you put 4 and 2. So imagine this is like the 0 and 1, right? So because we popped out or DQ'd 1. I'm just going to leave it here for reference. And then you pick up 4, you explore it completely, and then you will see that you have actually 3, right? Then 4 cannot be explored anymore. There is nothing in there anymore. We pop out 4, then we pick up, we DQ 2 to see what are the connections in there, and then you will discover that we have connection with 5, 7, and 8. So we have 5, and it doesn't matter like which order it is. So I just simply said 5, 7, 8. You could actually say 5, 8, and 7 if you want to. No, it doesn't matter. It will matter probably if you have something like, if you have weights on the graph and then you start actually like caring about like which one is going to come out first. Then 2, for example, in this case has been completely explored because you already know all the stuff. So you actually have been pushing 5, 7, and 8. And then you start again exploring 5, right? You pop it out and explore 5. 5 is actually connected to 6, right? And then you can actually push 6 if you would like to actually explore it later. We pop out 7. 7 actually doesn't have any connections anymore. Probably I forgot 9 to insert somewhere. Did I? Yeah, I forgot to put 9 somewhere. Hang on, where is 9 right now? So 1, 4, 2, 3, 3. Yeah, I forgot to explore 9 right now. So hang on. So 1, 4, 3, 1. So we have 1, 2, 4, 1, 4, 2. And then we pop out, for example, 4. So we're going to have 3. It's 10 and 9. Yeah, I forgot a number somewhere. Actually, I forgot to push 10 and 9. But I mean, you get the idea. So 4, 3, 3, 5, 10, and 9. So let me actually like take out these guys and let me push here 1, 4, 2, 3. So we have 10 and 9. Actually, I forgot to push them in. So 10 and 9, right? So 1, 4, 3, 10, 9. And then we get back to 2, which we need to explore. So it's going to be 8, 5, and 7. So 8. Oh yeah, so it's actually 5, 7, 8. Actually, I didn't push this into the stack, so I don't erase these numbers again. But we have already 8, 5, and 7. So 8, 5, and 7. And it hasn't been explored yet. And then 6 will be coming at the end. All right. So basically speaking, you are just simply like pushing stuff into the queue, you popping them out, and then you explore its children. This is what a BFS is all about. Here's the interesting part though. If you have a maze like this, let's say you have a maze that looks like, hang on, let me actually like pick up one. You can actually like generate mazes and stuff if you want to. It's actually one of these interesting applications. So if let's say you have a maze that looks like this. So we have node 1, node 2, and then you have something that looks similar to this. Or you can think of it like a maze or a city map. Let's say like so, maybe like so, just to make this as complicated as possible. Well, it's not that complicated at the end, I think, but I think it would be interesting to have. So let's say here, okay? So let's say it's going to be like so. Or 1, 2, 3, 4. Let's say so. I think it's good enough. Okay, and let's say that this is my goal, and this is my starting point. Okay, so you would like actually to reach this point ASAP, or actually getting the shortest path. So what you're gonna need to do here is just gonna simply say, okay, I'm gonna actually like, I'm actually visiting one, so I'm pushing one, right, somewhere, in a queue. And then you start exploring all the children, and then you have only one child, which is 2. So you pop this out from the stack, it's already done, or sorry, you dequeue it, and you are picking up 2, right? And then right now you have nodes, let's say 3 and 4, for example. So what you're gonna do is just simply like you push in, so you have actually 2 has been already pushed, 3 and 4, for example, right? So you actually DQ 2 because it has been completely explored. You already know all of its children, and right now, or all of its connection, right now we pick up, for example, 3. 4 already has been connected to everybody, and it has been explored by like 2 and 3 has been touched upon, so we don't need to even explore it further. So usually you don't explore a vertex that is being visited or has been visited. Just this is the main important point here. All right, so so 4 is actually like completely unnecessary step to check, but because of the algorithm, it's going to be checked anyway. But I'm checking it out so we don't actually confuse ourselves too much. And right now we're going to actually explore 3. So 3 has actually connection to 5, for example. Let's say here's 6, and let's say here is going to be 7, and maybe here's going to be 8. Okay. So this is, you know what? I actually could have, let me make this even a little bit more interesting. Hang on. Let me, sorry about that. Hang on. Let me actually make this a little bit more interesting so it just doesn't become as straightforward as this one. So we're going to still keep the same thing right now. I just simply like shifted the thing to the side. Okay. So it's going to be like, this is going to be still 6. This is going to be 1, 2, 3, and 4, 5, right? So it's, so we are still having the same steps. I just simply shifted it to the side just to make it a little bit more interesting. Okay, because if you are using depth first search in this, you would have actually explored like and went through the path. You would find the path to the end goal, but it's not the shortest. But with BFS, you would have actually found the shortest path. So as I'm mentioning here, so 5 here is 5 is positioned here. So 3 has been like has already 4 and 2 has been explored. 5 is going to be pushed into queued in. And then 5 needs to actually see, okay, so you have 7 and 6, right? So it has 7 and 6. And right now you will say, for example, okay, so 5 has been completely explored, cross it out. And right now we pick up 7. All right. 6 already has explored, like has already 8 as a connection. 7 is already needs to be explored. 7, once I actually see it here, it's actually connected to the goal. Right? So right now I've actually reached my destination because I already pushed this again. So I pushed this to like, I'm pushing this, sorry, to the queue. So 1, 2, then I move diagonally 3 because excuse me, because 4 has been already explored, 3 has been already explored. We pick up 5. 5 is actually pushing in 6 and pushing in 7. Excuse me. And then exploring 7, we got to the goal. So we don't need right now to explore 8 or any of that stuff. We already have reached our destination. Now, the key here is we need to traverse back. And the implementation detail for this is that you need to have a data structure to keep the parent node. So for example, if you have explored 1, right, and you went to 2, you have to say how I reached here. So once you are actually standing here, you say that node dot parent equal to the previous, right? So you're going to have, for example, if you have a class node, you're going to have, for example, parent, which is node parent, right? Get and set and whatever you would like to have. And then the other properties of your nodes, right? And then you just simply say your current node. So if this is the current node, your current node dot parent equal just to the previous. And you keep just simply adding that to the previous. So add to the previous, add to the previous, add to the previous, add to the previous. And what you need to do just simply once you reach to the goal, once you have the goal, you just simply say, give me the previous node at which I reached to you. So the previous node will be 7. So the parent or the previous is going to be this the 7. So let me just call it previous. Well, fine, let it be parent, fine. Anyway, I mean, we call it previous or parent. And then you go move back, and then you say, what is the parent of 7? It's going to be 5. And who is going to be parent of 5? It's going to be 3. And who's the parent of 3 is going to be 2. And who's the parent of 2 is going to be 1. You just simply keep pushing this into array, and then you just simply found your shortest path. This is basically like a very crude or just a quick overview of how to find a shortest path in a graph. Now, BFS is used in real life, I think, in navigation, but I think it's if you are doing actually game development or something like that, the most popular one is A-star, for example. And A-star is similar to it, but it uses heuristics. So it's a little bit more efficient in finding paths like from point A to point B in a weighted graph or a weighted map. So if you have, for example, like a higher cost somewhere in a graph to traverse, it will just simply ignore that path and it will choose the shortest and the most cost-efficient route. There is also something which is called the flow. Actually, like it's similar to some sort of a flooding algorithm to find the path between 2 points by flooding the actual graph. I forgot the name of it. There's something like object flow or something similar to it. Something has a flow word into it. Just I cannot remember it exactly. It's actually been used in the game called Bad North, where if you go on the internet and check out how the game is being played, you have right now like a bunch of soldiers moving on a terrain, and the terrain being selected. The terrain is actually a grid with obstacles in them, by the way. So it is exactly like a graph problem. And what the guys were doing, they had this interesting flow algorithm in order just to find the shortest path where these bunch of soldiers will actually flow and will start, following. They actually stand like in a batch like this. So they stand like in that order, for example. But when they start moving correctly in a path. And they actually do not intersect each other that much. They don't like go through each other. They just simply like flow on the terrain. And then once they reach their destination, they reorganize themselves back. So it's actually quite interesting algorithm. I think the guy has written a blog post on certain implementation details regarding this. So yeah, this is pretty much it regarding the regarding BFS and DFS, which I wanted to mention, besides the applications and other interesting facts about them. I will actually like stop recording right here.